Hello everyone, I'm Dr. Q. Welcome to my channel. In this video, we will talk about regressional analysis and how to read the regressional results. And as a manager in managerial economics, knowing the data, knowing the information provided by the regression of data is very essential for us to make optimal strategic decision. And we're supposed to be able to read the results and be able to interpret the regression output and use this, apply those information into our strategic decision. So regressional analysis is very important. As a manager, you need information to know about your what you're expecting about your products. For example, demand. Okay. How does a manager obtain information on the demand function of your products? If you're a t-shirts company, what is possible demand? If it's a furniture company, what's the possible demand function? You can collect information from published study from peer-reviewed journals, or you hire some consultant like economists or statistician. They use a statistical technique called regression analysis, using data on quantity, price, income, all the other influencing variables, and run regression and provide you the output. And as a manager, you're supposed to be understanding the output and interpret it. So this belongs to one of the branches of economics, econometrics. Econometrics is a statistical analysis of economic data. This is not an econometrics class. However, we like to know the basics about the regression line and the least squares regression. And we want to have plenty of examples demonstrated to provide you understanding of regression and how to read the statistics and how to interpret them. So give you an example of estimation of a demand function. Let's just assume that we care about the demand function. The true or population regression model with a whole population of dependent variable y, assuming y can be written as constant number a plus b independent variable x plus error term. So what those means? So in real world, we don't know the whole population. The whole population is unknown. Like, imagine this is a population of all the possible x and y combination. Those every dot over here is x and y combination. The population or the big data are huge and impossible to obtain. So even for a census every 10 years, decennial population survey, is the goal is to get every single resident's information. We wouldn't think that report is the true population, even though although it's very, very close. Okay. So those information are unknown. What we could do is collect data from the big population. So for example, we collect this sample of data within our capability. And this sample of data is used to estimate the possible using least square estimate for this unknown A. and unknown B. Okay. So the population is not accessible, but the sample we collect. And the bigger the sample, the more likely the sample is closer to the population, and the better the estimation, um, the A and B are, is closer to the true value. Okay. Um, that's why we like the big data. Okay, the bigger the better. The parameter estimates, we put a little hat on top of it, indicating it's an estimation of the true value. A and B are, we don't know, they're unknown because the big population is not accessible. From the sample, we use the least square regression line regression to figure out the estimates of A and B. A hat is estimate for A, B hat is estimate for B. So why is it called the least squares regression line? So these estimates A and B, A hat and B hat, represent values of A and B that result in the smallest sum of squared errors between a line and the actual data. So what that means, so imagine the data, actual data are those A, B, C, D, E, F. Okay. The econometrician's job is to find a smooth line or curve that does a good job of approximating the data points. So if you do a link, just link all those points A, B, C, D, E, F. The curve is very curvy. It doesn't do a good prediction of what's other things possibly be. We don't do a good, we provide inconsistent information of what's a vertical intercept is and what is the slope. So we want a smooth line uh, near all those points. How do we make sure that the line does a good job on approximating the data points of A, B, C, D, E, F? We'll make sure the distance between each point and the line, the vertical value, is the smallest. But because some of those values are positive, some of those values are negative, if you simply do a summation, they may cancel out, they may go zero. So how do we make sure their distance is smallest? We do a square, okay? We square the distance. Square distance turn negative to be positive. As long as the squared distance is the smallest, then we say this line does a good job on approximating the data points. Here's an example. How do we like run a regression and get approximate estimation of the, for example, vertical intercept and the coefficient? Here we got 10 observations. Of course, it's very small, just for demonstration. And for each observation, there's a pair of information for quantity and price. Let's say quantity, money, and price. And if you want to do the know the statistical data, you can run the average or median or mode of it. So for example, you can check average quantity. No quantity, or you check the average of price. An average price of $455. Now we want to do statistical analysis. There are so many nice statistical package. We have Stata, we have R, we have SAS, Python. Here we just use the spreadsheet as easy demonstration. Okay. What you normally do, some of those Excel does not um, just come with a statistical package. You need to install it. Okay, so you go to File, Options. You get on Add-ins, and you install one of those like Analysis Tool Pack, and go. You click on Analysis Tool Pack. Say OK, and this now the data analysis should be under Data. Okay, under Data. So you click on Data Analysis now. Then it pop into those options. You can do so many different things about it. And we want to select regression and click on OK. Then ask you what is your Y range, what is the dependent variable. You say quantity, select it. Now what is your X, what is your independent variable? Select price and make sure that as we select the label, you click on labels. Make sure they know that the first line or first row is variable name. And then you can click on other things, figure out the residues or plot the residues, plot line fit, or standardize the residue. You can do all of those. And click on, or you don't do anything, just figure out the coefficient. It doesn't matter. And you click on OK. You got the statistical report. Okay, statistical report. We have some statistic called R square or just R square. We got the F value and the significance of F value. R squares, statistical of F statistic and significance of F. And more important, we got intercept, vertical intercept coefficients, and the price coefficients. Okay, and we have quantity and predicted quantity, the true value and the predicted value. Okay, predicted value is like a more continuous, consistent line. Okay, let's say downward sloping, price and quantity move to opposite direction as expected. Now, I just copy and paste this portion of the report into this spreadsheet. They're the same. You can see they just made the decimal as two points decimal. Here you go. So 0.87, 0.75, 0.72, 112.22. So here we go. Okay. So what we care first is the coefficients over here. Having this, we can write down the estimates of vertical intercept and coefficient in front of a price. Those are estimates, and write down estimated demand function. Quantity equals to the vertical intercept minus 2.6. multiply price. So this gives us the nice estimate demand, and we can use this to do the calculate elasticity and figure out the total revenue and all that. And with a different sample from the population, we're likely to have different estimates. If the sample is very large, we have big data, it's very likely that we have a good estimation of A and B to true value. And if there's no bias selection, generally speaking, different sample will yield different estimation, but they're supposed to be close to each other. Now there are several statistic values I want to emphasize because it tells us the statistical significance. The first one is called the standard error. Because, as I said, the different sample got different estimates. The standard error measure how much each estimate varies in regression based on the same true demand model using different data. The standard error gives a measure of how well a sample represents the population. When the sample is representative, the standard error will be small. Okay. So if we have a big population, and if we do a good job and we do a good job on collecting data, then the standard error is supposed to be very small. But if you just collect small amount, it's very likely that the estimates are far from the true value. Okay. And the for a standard error, the smaller the better. Then the second one is a confidence interval. Is also measuring the how significant the how well the sample are representing the total population. And generally speaking, it is the estimates upper level, upper confidence interval. The upper cap is estimates plus 2 multiply standard error of the estimates. The lower bottom minimum is alpha minus 2 multiply the standard error. And generally speaking, the tighter, the better. The intervals are smaller, the better. Let's look at an example. Here are some estimation. The dots over here estimation. The confidence interval hover around its coefficients. We can say this area, the confidence interval are very tight, it's great. And after that, we can see it's spread out. Okay. Next one, the T statistic is very important. T statistic measure the statistical significance of the estimate coefficients. Generally speaking, if the absolute value of t larger than 2, we say the results are significant, statistically significant. Of course, the bigger the better. So we can see the standard error here is relatively small over here for the price compared with the the coefficient. And the t statistic, we can see absolute value 6.69 larger than 2. Absolute value 4.89 is larger than 2. We say the intercept is statistically different from 0, is significant. Okay. I mean, here's the coefficient. Standard error is 243.97 for the vertical intercept. Standard error for coefficient is 0.53. Next one, we want to check if we include enough of explanatory variables in our regression. Do we have enough x's on the right-hand side? So for example, quantity demand is not only influenced by price of the product, but also by price of other products, income, preference, and awareness. Advertisement promotes awareness of the brand. So do we include all of those possible explanatory variable? So R squared tells us the information. It is a fraction of total variation in the dependent variable that is explained by the regression. So let's say R squared is 0.67. So 67% of the variation on the dependent variable are explained by the regression. It is also called a coefficient of determination. Okay. So sum square in regression over sum square of total variation. And R square range from 0 to 1. The bigger R square, the better. The closer, the value close to 1 indicate a better fit. Means majority of the variations are explained by the regression. But there's issue with the R square. Sometimes R square is close to 1 if the number of observations is small relative to the number of estimated variables. So you have, like, for example, 8 independent variables, and you only have 10 observations. This is not good. It's really not good. You want to have a much bigger number of observations than the number of variables in explanatory on the right-hand side. So economists or econometrician developed this adjusted R square thing. Adjusted square R square is a version of the R square that penalizes researchers for having a few degrees of freedom. What's the meaning of few degrees of freedom? Means your number of estimated coefficients is very close to the number of total observations. They're too close. The difference between the two of them, the bigger the better. Okay. And the number of observations minus the number of estimated coefficients is the degree of freedom for the regression. So whenever this n and k, the number of observations and the number of estimated coefficients are very close to each other, the denominator is very small, therefore the ratio is very large. And 1 minus r squared is smaller than 1. So this is very large. this whole thing is very large. 1 minus very large, the r square, adjusted r square is very small, even though the r square is here is big. So adjusted r square, we put an upper bar over here. Adjusted r square is the number of estimate variables must be smaller than the number of observation to have adjusted r square. We're going to see adjusted r square is over here. They're close, but we generally speaking trust adjusted r square better than r square. Next one is F statistic. It is a measure of total variation explained by the regression relative to the total unexplained variation. So as opposed to explained variation over total variation, is a ratio between explained variation over unexplained variation. It's very similar to R squared. Generally speaking, the greater the F statistic, the better the overall regression fit, means the explained is much bigger than unexplained. And there's a, how do we check how the F statistics is big enough? We have a F significance value. It's also called a p-value. Is another measure of the F statistics. Generally speaking, the bigger the F statistic, the better, but the lower, the smaller the p-value, the better. P-value smaller than 5%, 0.05, generally speaking, associated with the better overall regression fit. Okay. So we can say F statistics 23.94 is pretty big. To further validate it is a significant good fit, we can check the significance of F. It's also called a p-value. Okay, it's also called p-value. We can see this is a 0.0012. It is smaller than 5%, smaller than 0.05. So it means it's significant. It's good, overall good fit. Okay. Sometimes we have a nonlinear situation. We talked about this before. We have the log or log linear, which means the left-hand side dependent variable is in the natural log format, and the right-hand side, the price, is also in the natural log format. And we say the coefficient in front of the price, natural log of price, is the elasticity. Beta p is the elasticity of own price, elasticity of demand. So how do we do about those? How do we figure those, run those type of regression? It depends. Depends on if you have the raw data already in its natural log form. If we have the data not in natural log form, for example, here's just absolute value, number of tickets sold, and here's the ticket price. It is not in its natural log form. The first step, if you want to run a log-log regression, the first step, you need to transform it. Okay, transform the quantity into natural log of quantity. In statistical packages, it's very easy to do. For example, in Excel, so we want to figure out what's the natural log of 18. You simply input equal log, natural log ln, and the corresponding value. Okay, you figure out 1, you popularize everything, you got the natural log for all the quantities. The same for the price. You take a natural log of the absolute value of price, and you popularize everything, and you got the natural log of price. Then next, you just follow a step like what we did. Make sure you have the statistical package installed. you do data analysis on regression. Okay. Now your input of y is the natural log of quantity, and your input for x is the natural log of price. And you make sure you click on label and you run a regression, and you got this estimation of coefficients. And this is the elasticity over here, right? And this, you got a standard error, you got t statistic, we can say they're significant as absolute value bigger than 2, and p-value very tiny, very small, which is good. And we can see r square is very large, good. F value very large, good. And the statistic significance of f, p-value is very tiny, which is great. Okay, and the confidence interval is pretty tight. Now, um, generally speaking, we have more than one independent variable. As we said, the quantity demanded for product X is not only influenced by the price of X, it's influenced by multiple variables. So we have a multiple independent variable on the right hand side, and we have this regression. Then this regression is called multiple regression. Multiple regression. Okay. And what to do about that is the same, and we can just demonstrate for you. So for example, here we have 10 observations, and we have quantity, and we have 3 independent variables influenced by price and influenced by how much effort the producer devote on promote awareness of the brand advertisement, and the distance between consumers and the destination. And we ran a regression just like what we did. Make sure you have the data statistic package installed, and we have regression. Click on regression, and now the y range is still 1 quantity, and the x range now is the 3 of them. Make sure you highlight all 3 of them, and make sure all your x's independent variables are adjacent to each other. Adjacent to each other is easy to select. And make sure you click on label, as we did include label, and we run a regression. Now we got the multiple coefficients, the coefficient in front of price, advertising, and distance. We can say the advertising statistics t-value is not very large, is absolute value smaller than 2, so we say this is not statistically significant. Okay. Adjusted R square is decent, 68.7% variation are explained by the regression. F value is decent, and this p-value significance of f is smaller than 5%, 0.05, so it's okay. Of course, you can run multiple log linear regression as well. Okay. And if we just copy this into the spreadsheet, we got that. Okay, just as I described, t-value for advertising is small, saying this is not statistically significant. That's all I have for today's video. Thank you for watching. I will see you in the next one.